Okay, so we're going to look at limit properties today, and I'm just going to start with example, okay? Limits can be added or subtracted or multiplied or divided or multiplied by a constant, just like you would normally think they would, okay? So this is actually going to be pretty easy, all right? But let's just start off with an example here. Let's say that you're given that the limit as x approaches 2 of f of x equals 3, and the limit as x approaches 2 of g of x equals -4. Okay, so you're given those two things. And you could be asking questions about that. So, and this is going to be pretty obvious. Limit as x approaches 2 of f of x plus g of x, that whole thing. Guess what that's going to be? -1. Yeah, it's that easy. Okay? So you can add the limits. Now, what has to remain the same though? You see here.
The number.
Yeah, we gotta be looking at the same point, okay, which is the number that x is approaching. So if this question said as limit as x approaches 3 of f of x plus g of x, there's no way you don't have any information to deal with that. But as long as it's the same point, then you just treat it like you normally would with adding and subtracting. Okay. So let's just run through a few of these. Limit as x approaches 2 of f of x minus g of x would be what? 7. Okay, times limit as x approaches 2 of f of x g of x is going to be -12, so and so on. Okay, you can divide, you can multiply by a constant, so let me do one of those. Limit as x approaches 2 of f of x over g of x, that would just be 3 over -4, or -3/4. Okay. I did divide. I said multiply by a constant. Let me do that one. Limit as x approaches 2 of 5 f of x. That's just going to be 15. Okay. This might seem really easy, but we're going to kind of, make it a little more complicated with something like, let me divide this. The limit as x approaches 2 of x f of x plus 6 g of x plus 10. Okay, so that's more along the lines of what you're going to have to do. Okay, so this x right here, that's just this x. Alright, so the x is 2. Alright, so that's 2. And then the limit as x approaches 2 of f of x, we're getting from here, that's 3. Alright, so that's 2 times 3. And then plus, so basically you just break this up into each part. Alright, plus 6 times what we have for the g of x, which is -4. And then this plus 10 is just going to stay at plus 10. The limit as x approaches 2 of 10, there's nothing to plug the x into, so that's always 10. Okay, so then you just add those up. That comes out to -8. All right. Any questions on that? Pretty straightforward. You won't get something this simple over here, but this last one, that's the kind of the level of stuff you have to do. Okay.
Why have to come
This x right here, this x is this 2. Because x approaches 2, and we're just plugging in the 2 for that x. And then the f of x is 3, the 6 is still here, the g of x is 4, and or -4, and the 10 is there. Okay. All right, now there is a special case that we want to look at of this is a special case. For some reason, this comes up a lot. Okay.
What's the name of it?
Yeah, I don't know, that's just what I call it. The limit as x approaches 0 of sine x over x. Let's graph that so we can see it. Okay, so if we look at sine x over x, and I kind of want to zoom box that. Okay, so that is the function sine x over x. What is the limit as x approaches 0 of that? Looking at that graph. No, that's actually 2 right there. Sorry, you can't really see, but that's 1, okay? It's 1. Now, what should there be right here at x equals 0? What should there be if you were to graph this yourself? There would be a hole there. The calculator doesn't show it, but there should be a hole there because, why should there be a hole there? Because you can't put in 0 for x, because that gives you 0 on the denominator, okay? So there should be a hole there. But the limit is 1. So instead of what we just saw on the graph, really this graph looks like this, okay? It's just the calculator doesn't show where the hole is, okay? But the limit is still 1 because it approaches the same y value from both sides. All right. So we can use the rules that I just talked about along with this special case to get any limits that involve the sine x over x. Okay. So let's say we have the limit as x approaches 0 for sine x over x. Well, the sine x over x part of it is just 1, all right? And we're multiplying that by 4. So the answer to that will be 4. Okay? Everybody see that? All right. It also happens to work out, and I'm not going to get into exactly why, but if you have sine 4x over x, it works out the same way. Okay, it works out the same way. That's still 4. Right. But let's look at some more interesting ones here. That's always better. Let's say we have the limit as x approaches 0 of sine squared x over 3x. Okay? When you have something like this, what you want to do is you want to isolate the part, you want to isolate a sine x over x, because that way you can cancel it because that's 1, all right? So we want to isolate sine x over x so that we can cancel it, all right? So we could say, what could we do to do that here? Limit as x approaches 0. How could we rewrite this to isolate a sine x over x? This is sine squared, so there's really sine times sine there, right? We have a 3 and an x on the bottom. We want to take one of those sine x's and put it with the x on the bottom. So we can rewrite this sine x over x times whatever's left, which would be sine x over 3, right? Okay, that's the same thing. It's just rewritten. But what we want to do is we want to isolate this so that we can cancel it, because that's going to be 1. Alright? So then we're left with just sine x over 3, and now what can we do? We can just plug in the 0 now. Okay, so we plug in the 0 here. Sine of 0, you should know, is 0. So 0 over 3 is 0. Okay? So let's look at a couple more like that. Limit as x approaches 0. Notice how x always has to approach 0 for this special case of sine x over x. Okay. Let's say it's sine x over x squared plus 3x. How can we get a sine x over x out of that? What do you think? Okay, yeah. So you factor out an x out of the bottom. So you gotta look for stuff like that. Okay? You factor an x out of the bottom, alright? So that's the same thing as the limit as x approaches 0 of, we're going to factor an x out of the bottom, so sine x over x times x plus 3, right? And now here is our sine x over x, so that cancels. What's left on top here? There's a 1 left on top, right? So there's still 1. So, and then we can plug in our 0 to the x, and so we get 1/3 there. Right? Now don't forget, what does this 1/3 mean? What does that 1/3 tell us? When you say where, on the y, yeah. So that is the y value where this function hits. It would hit a value of 1/3 at 0 if there wasn't a hole there. Okay. So basically, whenever you're doing algebraic manipulations to things and canceling stuff and then plugging in the number, you're getting the y value where the hole is. You're getting the y value that the function would hit if there wasn't a hole there. Okay, at that x value. Okay. Let me do one more of those. Limit as x approaches 0. Let's say 5x plus sine x over 3x. Okay, so what can we do with this? That's a 5 right there. 5. So remember, we want to get sine x over x. Now, if you have one term in the denominator and two terms on top, you can just split that up. They both go over that denominator. Right? When you add fractions, you keep the denominator the same. So you could rewrite this as 5x over 3x plus sine x over 3x. See, if you add 5x over 3x and sine x over 3x, you get 5x plus sine x all over 3x, right? So this is one trick that you might have to do sometimes. You might have to split up a fraction. Now you can only do it if the denominator is just one term. If the denominator was two terms, you can't split those up. That's a much longer process. Okay. But if the denominator is one term, you can split the top up, put them both over that denominator. Okay. So now what do we have here? We can cancel these x's. So I just have a 5/3 there. And I have a sine x over x can cancel, and I'm left with 1/3 here. Right? So 5/3. Now there's no more x to plug in. Yeah, so 5/3 and 1/3, that'd be 6/3, which would be 2. Okay. Now there's going to be a couple of problems that are might look complicated that there really aren't. Okay, like let me give you an example of that. Don't be scared when you see this stuff. Square root of 2x plus e to the x over log base 3 of x plus 9. Alright, that looks kind of bad, alright? But don't get scared of it. Remember, what's the first thing you're always going to do on a limit problem? Yeah, just plug it in. Plug in, so in this case, plug in the 0, right? Okay, so that's just going to be 0 plus e to the 0, right, over log base 3 of 9. So e to the 0 is 1. Log base 3 of 9 is 2. So there's your answer. Okay, so just because it looks complicated, doesn't mean it is complicated. Okay? Okay. Yeah.